This lecture is going to pick up where we left off last lecture with the sampling distribution of the sample mean and the t-distribution, and take a look at how we can start to do inference on population means. So consider this situation. Let's say we take a water sample from 6 different locations in Flint, Michigan. Flint, if you recall, had this big water crisis several years back whenever they had unhealthy drinking water. And what we want to do is we want to estimate the average pH balance of Flint's drinking water. So the way that we can go about this is to use a confidence interval for a population mean. We can take a random sample from the population, a random sample of different water locations in Flint. We can find the sample mean. Because the population standard deviation is unknown, we'll have to use the sample standard deviation instead. We can then check the conditions to see if the t-distribution applies, and then calculate upper and lower bounds for a confidence interval to give us a range of plausible values for where the average pH balance of Flint's drinking water is likely to fall. Now, to estimate a population mean mu using a confidence interval, what we can do is we can center the interval at x bar, add and subtract some critical value from the t-distribution that has n-1 degrees of freedom, and then multiply that by s, our sample standard deviation, divided by the square root of n. Now, this confidence interval is only going to be appropriate if the following conditions are met. We have to have independently sampled observations, we have to have a random sample, the 10% condition must be satisfied in that the sample is no larger than 10% of the population, and the nearly normal condition also must be satisfied. We have to make sure that the distribution of the sample mean is approximately normal using the conditions that we saw in the central limit theorem. So let's consider the first 3 conditions. If we're going and we're taking water samples from 6 different locations in Flint, then these locations are not going to be perfectly independent because they're all in or near Flint, Michigan. But if we choose these samples specifically so that they're far enough away from one another, then we can consider them to be independent enough. As with the independence condition, the randomization condition is probably going to be okay if we don't deliberately choose specific locations so as to introduce bias. So we may look to choose locations that are far enough away from one another, but we don't want to specifically choose locations that we know are going to have unusually high or unusually low pH balances. And Flint is a fairly large city, so there are definitely more than 60 locations that we could choose from, so by taking a random sample of size 6, the 10% condition is also going to be satisfied. Now, the pH balances of our 6 observations are contained here in column A. We have a maximum of 8.3 and a minimum of 7. Taking a look at our statistics, that gives us a sample mean of 7.75, a sample standard deviation of 0.48, and a sample size of 6. These statistics can be found using the average function in Excel, the sample standard deviation function in Excel, which is stdev.s, S standing for sample standard deviation, and the count function. The argument that goes inside of these formulas is just a column of data, in this case column A. Now, looking at the histogram in the bottom left, we can see that our 6 observations form what looks to be a pretty nice normal distribution. It's about as close to normal as we can possibly get with only 6 observations. As a result, because the histogram is as normal as possible, given only 6 observations to work with, we can say that the nearly normal condition is going to be satisfied because the shape of the histogram is approximately normal, even though our sample size is smaller than 15. Now, going back to this slide again, we already know that the sample mean is 7.75, the sample standard deviation is 0.48, and our sample size is 6. This gives us 3 of the 4 values that we need in order to calculate out this confidence interval. The last value that we need is going to be our critical value from the t-distribution. Now, we have 6 observations here, meaning that we're going to have n-1 or 5 degrees of freedom. Looking at our t-table, if we intersect the row for 5 degrees of freedom with the column for 95% confidence, we're going to end up with a critical value here of 2.571. So setting up our confidence interval, again, we know that we're going to have 5 degrees of freedom. And our confidence interval is going to be centered at 7.75. Then we're going to add and subtract the margin of error, 2.571 times the sample standard deviation of 0.48 divided by the square root of our sample size, the square root of 6. Now we found this 2.571 directly from the t-table. You also have the option of using the function in Excel, t.inv.2t, in order to find the critical value here. Using this function requires you to put in 2 different arguments. The total probability that you want to leave out is going to be your first argument. In this case, because we want 95% confidence, we're leaving out 5% of the area, so we put in 0.05 as the first argument. The second argument in this function is the number of degrees of freedom that you have. Working out the margin of error is going to give us 0.504. So we have a final confidence interval of 7.246 as our lower bound and 8.254 as our upper bound. Now, interpreting a confidence interval for a population mean is very similar to what we did for interpreting a confidence interval for a population proportion. We have a level of confidence, we have a parameter that we're talking about, and we have upper and lower bounds. So what we can say here is that we are 95% confident, or we can say with 95% confidence that the true pH balance of the drinking water in Flint is between 7.246 and 8.254. Now we can also use this confidence interval to answer different questions. The pH balance of water should be 8 whenever it's safe to drink. So we want to know if it appears as if the water in Flint is safe to drink. Considering the confidence interval that we have, the confidence interval contains 8, which means that 8 is a plausible value for the mean pH balance. And because 8 is a plausible value, that tells us that it does appear as if the water is safe to drink. 8 is a plausible value for the mean pH balance, meaning that the pH balance is at an appropriate level to consume. Let's discuss the implications of choosing a different level of confidence. Now, notice for our 95% confidence interval, we had a critical value of 2.571. This is considerably larger than the critical value of 1.96 that we would typically use when using the standard normal distribution, when using the z-distribution. Let's say instead, though, we choose 90% confidence, and we wanted to calculate out a confidence interval here. Well, because we want 90% confidence instead of 95%, we need less area in the middle of our t-distribution. As a result, we'll end up with a narrower confidence interval. We'll have a smaller critical value multiplier. Our critical value here would be only 2.015, giving us a confidence interval of about 7.355 up to 8.145. Now, on the other hand, if we had chosen 99% confidence instead of 95%, we would have ended up with a wider confidence interval. This would have given us a larger critical value of 4.032 compared to the 2.571 that we used, meaning that our confidence interval would have ranged from 6.96 up to 8.54 if we went back and redid the calculation. The only thing that changes whenever we go to either 90 or 99% is the value of that critical value. The sample mean stays the same, the sample standard deviation stays the same, and the sample size stays the same. Now, if we wanted to determine if we would come to the same conclusion about the average pH balance regardless of the interval, in this case we would end up coming to the exact same conclusion. All 3 of these intervals contain 8, meaning that regardless of the confidence level, in these 3 cases, all 3 of these intervals would have indicated that the water is safe to drink. In addition to being able to calculate out a confidence interval for a population mean, we can also perform inference for a population mean using a hypothesis test. So if you have a single unknown population mean, and you have a particular hypothesized value in mind, we can do the hypothesis test. The conditions for doing this hypothesis test are the exact same four conditions that we needed for the confidence interval: independence, randomization, 10%, and nearly normal. Our test statistic in this case is going to follow a t-distribution with n-1 degrees of freedom, and we'll calculate out that test statistic by taking the sample mean, subtracting off the hypothesized mean, mu naught, and dividing by the standard error, s, the sample standard deviation, divided by the square root of the sample size. Let's take a look at an example. A recent study found that high school students who work more than 15 hours per week are more likely to drop out of high school. Let's say we take a random sample of 16 high school students who have part-time jobs, and our goal here is to determine if high school students who have part-time jobs are working significantly more than 15 hours per week on average. So here we're doing inference on an unknown population mean. Mu represents the average number of hours worked by a typical high school student who has a part-time job. And our hypothesized mean here is going to be our cutoff for when students are more likely to drop out, which is 15. So we can set up the null hypothesis as mu equal to 15, meaning that high school students are not working too much, versus the alternative, that mu is greater than 15. High school students are working too much. Whenever we take a look at the conditions, the independence condition almost certainly holds. One student's hours at work likely do not impact how long another student works. If we take a random sample from employed high school students, this is probably a pretty good representation of the overall population of high school students who have a job. We have a random sample of size 16. There are certainly more than 160 students out there who have part-time jobs, so the 10% condition holds. And looking at the histogram of our results over on the right, what we see is that the histogram is pretty close to being normal. The peak in the center is a little bit taller than we would typically expect, but it's unimodal, it's very close to being symmetric. Moreover, we also have more than 15 observations. So the nearly normal condition is satisfied because the histogram is approximately normal, and our sample size is greater than 15. We actually satisfy the nearly normal condition in two different ways here. So looking at the data in Excel, we can now calculate out all of the statistics that we need in order to get the test statistic. Our sample mean is 17.5. We have a sample standard deviation of 5.5, and we have a sample size of 16. We also know here that our hypothesized value is going to be equal to 15, so we have all four values that we need for the test stat. Calculating out the test statistic, what we end up with is our sample mean, 17.5, minus the hypothesized mean of 15, divided by the standard error, 5.5, over the square root of 16, which gives us 1.818. This is telling us that if the true population mean number of hours worked per week by high school students is actually equal to 15, then our sample mean of 17.5 is about 1.8 standard deviations or standard errors above what we would expect. Now we have 16 observations in our sample, meaning we have 15 degrees of freedom. This then allows us to go and calculate out the p-value using Excel. Cell D8 contains a calculation of the test statistic. What you see in column E is the exact formula that you can use in order to calculate out the test stat. D2 is the sample mean, D6 is your hypothesized mean, D3 is the sample standard deviation, and then D4 is the sample size. Now, like I mentioned in the previous lecture, the only way to calculate out exact p-values or exact probabilities using the t-distribution is by using software. There are three different functions that you would need to use in Excel in order to calculate the p-value for the t-distribution. If you have an upper one-sided test, like you have in this situation, the function is t.dist.rt, rt standing for right tail. The two arguments that you put in there are the value of the test statistic and then the degrees of freedom. So in this case, we have 1.818 as our test stat and 15 degrees of freedom. If, on the other hand, you have a lower one-sided test, you use the t.dist function. There are three arguments. Again, you'll put in the test stat, the degrees of freedom, and then the third argument is always going to be set equal to true. For a two-sided test, you have t.dist.2t, which is the same function that we use to find critical values for the confidence interval. We can put in the test statistic and the degrees of freedom to again get the corresponding p-value. Now in this case, by using t.dist.rt, we see that the area up above 1.818 in a t-distribution that has 15 degrees of freedom is 0.0446. So as we said before, the p-value of this test, or the area up above 1.818 in a t-distribution that has 15 degrees of freedom, is 0.0446. What this actually means in context is if the true population mean number of hours worked by high school students who have part-time jobs is actually equal to 15, if 15 is actually the true mean, then the probability that we would get a sample mean of 17.5 or larger is 0.0446, a relatively small probability. In terms of coming to a conclusion, we can take a look at our p-value of 0.0446. We see that that is less than our typical 5% level of significance that we use. So we can say that we will reject the null hypothesis and conclude that the average number of hours worked by high school students who have part-time jobs is significantly more than 15 hours per week. This is also allowing us to conclude that high school students on average are at a higher risk of dropping out of school if they have a part-time job. Now, one important ability that you should be able to develop is the ability to look at an output and understand what's going on in that output, understand what's going on with someone else's results. So let's take a look at a hypothesis test that's already been performed. A recent study found that Americans spend an average of 171 minutes on their cell phones each day. We take a random sample of 25 college students, we ask them to track their usage for a day, and then self-report the number of minutes that they spent on their phone. We want to know if 171 is a plausible estimate for the average amount of time that college students spend on their phone using a 1% level of significance. Now, looking at the context here, we're just interested in if 171 is a plausible estimate. So here, this makes it sound like we're going to use a two-sided alternative. We'll use mu equal to 171 in the null hypothesis and mu not equal to 171 in the alternative hypothesis. Now, looking at the output, we have a test statistic of 3.31. We take our sample mean of 218 that was reported by the college students, subtract off the hypothesized value of 171, divide by 71 over the square root of 25, and that gives us 3.31. In order to figure out the p-value, we have to think about what the alternative hypothesis is here. Because we're using this two-sided alternative, that means that we need to use the two-tail probability, which is 0.0029. In terms of our conclusion, comparing our p-value to our level of significance, we see that the p-value is less than 0.01. So we're able to reject the null and conclude that 171 is not a plausible estimate for the average number of minutes that college students are spending on their cell phone in a typical day. And based on the results from the sample, it appears as if 171 is a little bit too low. The sample mean was 218, the hypothesized mean was 171, so it looks as if college students spend significantly more time on their phones than the hypothesized value of 171. Now, maybe a better question to ask at this point is if a two-sided test was actually reasonable to use to begin with. Based on what we know about college students, probably not. And the reason for this is that college students tend to spend a lot of time on their phones. So before we even set up these hypotheses, we probably should have suspected that the mean was going to be higher than 171, and we probably should have used an upper one-sided alternative. We probably weren't going to find a sample mean less than 171. So even if the sample mean didn't end up being too far away from our hypothesized value, chances are it was still going to be greater than 171. So the takeaway here is that we can always use a two-sided test, and they're best used if you're trying to hedge because you don't know much about the population. However, if you have some kind of a hunch about the direction of the alternative, if you have additional information that you know about the population, it's always best to use that one-sided test instead. That just about wraps it up for the one-sample t-test, but let's now take a look at a similar type of situation. Let's say we have a group of 9 amateur golfers, and they take lessons for a week at a golf camp. They play a round of golf at the beginning of the week, and again after they take their golf lessons. Each time they record their score. We want to know if the golfer's scores improved after taking the lessons for a week. So notice what's going on here is that we are comparing quantitative data across 2 levels of the categorical variable. Our categorical variable is when the round of golf was played, and our quantitative variable is the golfer's score. However, notice here that these 2 samples are not independent. Using the same people in each sample, keeping the same set of 9 golfers, and having them each record 2 different observations causes this dependency between the samples. What we're also trying to do here is look to see if there was some improvement in the before and the after scores. The inferential technique that we're going to be using here is called the matched pairs test, or inference for paired data. Here's what a matched pairs test looks like. We start out with our population of interest, and we take a random sample from that population. The first thing that we do is we ask these subjects to perform some kind of a task. We record their result at the end of performing this task, and we calculate their sample mean. We'll call it X bar before. Then, each subject undergoes some kind of a treatment or some kind of a training session. And after that's done, we ask them to repeat the task. We record their result again, and we get X bar after. In a matched pairs test, what we then do is we take the difference between each subject's before observation and their after observation and calculate the difference between them. Averaging out those differences is going to give us X bar for the differences. And so our ultimate goal here is to determine if there's a significant difference in the before and after mean results. More formally, here is what inference for paired data looks like. Inference for paired data is used for performing inference on 2 dependent samples where the observations can be paired with one another. And you're really looking to see if the pre-treatment and post-treatment means are significantly different. The conditions that we need here are, again, similar to what we saw with the one-sample t-test. We need independence, we need randomization. However, 2 of the conditions are a little bit different. We need to make sure that we have paired data, meaning that the observations are in 2 dependent samples and they can be matched with one another. The other thing that we need is, again, the nearly normal condition. However, the only thing that needs to be satisfied for the nearly normal condition is that the distribution of the differences is approximately normal. We don't care what the original samples look like. We're just concerned about what's going on with the differences. The test statistic here is actually identical to what we just did in the one-sample t-test, only we're working with the differences. We take the sample mean of the differences, subtract off the hypothesized difference, which is typically set equal to 0, divide by the sample standard deviation of the differences over the square root of the sample size. This is again going to give us a t-statistic that has n-1 degrees of freedom. So back to our golfer example. We have our 9 amateur golfers. They each take lessons for a week at a golf camp. They play 1 round of golf at the beginning, and then again after the lessons to see if they've improved. And that's really our goal here, is we want to see if the scores improved after having taken the lessons for a week. Now, in golf, lower scores are better. It means you took fewer strokes to complete the 18 holes. Our null hypothesis in a matched pairs test here is going to be that the before mean is equal to the after mean. Another way of writing this would also be to subtract the after mean over to the left-hand side. So we have the before mean score minus the after mean score is equal to 0. A third way of writing this out is to replace mu sub b minus mu sub a with mu sub d, where mu sub d represents the difference between the means. Any one of these three is an appropriate way to write the null hypothesis because they all represent the notion that there is no improvement in the scores. If the null hypothesis is true, we're saying that the before mean and the after means are equal, meaning that the golf lessons didn't actually help. Alternatively, what we want to see is that the mean score before having taken the lessons is greater than the mean score after having taken the lessons, meaning it took these golfers more strokes to complete the course before taking the lessons than it did after the lessons. As before, we can subtract mu sub a over to the left-hand side and say mu sub b minus mu sub a is greater than 0. Or a third way of writing it is to say that the mean difference mu sub d is greater than 0. Again, any one of these three is appropriate because they all represent the idea that amateur golfers are going to score better after having taken the golf lessons. Now, there's a lot more going on whenever you have a matched pairs test because there's more data that you're working with. So here's what's going on in these columns up here. Columns B and C contain your original data. Column B has your before data. Column C has the after data after having taken the golf lessons. What we're actually interested in doing here is performing inference on the differences. So rather than looking at the 80, the 72, the 81 for the before scores, or looking at the 78, 71, 75, etc. for the after scores, we're literally taking the difference in the before and the after scores using the formulas that you see in column E. We're taking the before score, subtracting off the after score to get the improvement in the golfer scores. Notice that positive numbers here are representative of the golfer performing better after having taken the golf lessons. Negative scores mean that they actually scored worse after the golf lessons. We also need to use IDs in order to keep the data organized here. You can't be taking the before score for golfer 1 and subtracting off the after score for golfer 3. You need to make sure that you're keeping these observations nice and consistent. Notice over on the right with our histograms that the before and after scores aren't anywhere close to being approximately normal. The after scores aren't terrible, the before scores really don't look as if they're anywhere close to being normal. That's perfectly fine because we don't actually need these histograms to be approximately normal. Even though we only have 9 observations, the only histogram that we are concerned about is the difference histogram down on the bottom right. This histogram does look as if it's approximately normal, which is exactly what we need. So the takeaway here is that the differences between the samples can be normal, even if the original samples are not. Now looking at our statistics here, we have a sample mean golf score of 75.4 for the before scores. We have a sample mean of 73 after, meaning that on average, these golfers improved by a little bit less than 2.5 strokes after having taken the golf lessons. One of the nice things about using Excel for the matched pairs test is the fact that you no longer have to write out your own formulas to get the results of your hypothesis test. You can install the data analysis Toolpak, which will allow you to perform a lot of these more advanced inferential techniques. I'll post a couple of links to videos where they show you how to install the data analysis Toolpak depending on if you have a PC or a Mac. Once you install the data analysis Toolpak, you can click on the button and it'll bring up the window that you see in the top left. For matched pairs, what you want to choose is t-test paired to sample for means. Clicking OK will bring up the dialog box that you see down in the bottom left. Variable 1 range is going to be for your before sample. Variable 2 range is going to be for your after sample. So in our data set, we have the before data in column B and the after data in column C. Down below, you will type in your hypothesized mean difference, which is typically set equal to 0. We're typically just interested in if there's a significant difference between the means of our two samples. Because we have before and after in the top row of our data, we want to check the box that says labels, and we can then go ahead and click OK. Once you click OK, Excel will bring up a new sheet at the bottom with all of these results. So you see the mean for each of our samples. These are the same means that we saw whenever we calculated them out by hand using the formulas on the previous slide. You have the sample variance, number of observations, and then you start to get the results of your test. We have 8 degrees of freedom here because we had 9 observations. The test statistic is going to be 75.444 minus 73 divided by the standard deviation of the differences, which is actually not reflected here in this output, over the square root of the sample size, which is 9. That's going to give us a test stat of 3.192. And because we have an upper one-sided test, we have a one-tailed test, we're going to use the p-value 0.0064. So working through the rest of the test, we have to first look at the conditions. We know that we have paired data. The data contains scores from the same set of 9 golfers at 2 different time points. We know that we have independence. One golfer's improvement from the lessons is probably not going to impact another golfer's improvement. We probably have a random sample as well. It's possible that the golfers may have known each other, they signed up for the lessons together, but they still technically comprise a random sample from the population of all amateur golfers. And going back to the histogram of the differences, that histogram was approximately normal, so the nearly normal condition is satisfied. Even though our sample size is less than 15, the shape of the histogram of our differences is close enough to being normal that we can make the assumption that the central limit theorem is going to hold here. Now going back and calculating out the test statistic, what we're going to do is take the sample mean of the differences, which was 2.444, subtract off our hypothesized difference, and then divide by the standard error. This 2.297 that you see here is not coming from the Excel output. The Excel output didn't give you the sample standard deviation of the differences. If you want that value, you actually have to go back into your original data set at the differences. Look at the differences that were in column D and calculate out the sample standard deviation in that particular column. That sample standard deviation from a couple of slides ago is 2.297. We divide that by the square root of 9, and that gives us our test statistic of 3.192, which we saw in the Excel output. We also saw that we have 8 degrees of freedom, and the corresponding p-value here is 0.0064. What we're saying is that if there really is no improvement in these golfer scores, then the probability that we would see an improvement of 2.444 strokes or better is only 0.0064. So in the end, with a p-value of 0.0064, we're able to reject the null hypothesis. Our p-value is less than 0.05. That allows us to conclude that golfer scores were significantly lower after having taken the golf lessons. In the end, they were significantly better golfers. They did perform significantly better after taking the lessons. Now let's suppose that we actually had a 10th golfer, another golfer who began the week and played the first round but had to withdraw from the golf lessons due to injury. We need a strategy for what we should do with this one observation here. Now, in a match pairs test, we really only have one option, and that option is to remove this observation in its entirety. We have a beginning score, but we don't have anything that we can pair that observation with, so we can't actually find the difference in the before and the after scores. We can't measure this golfer's improvement. This is an incomplete observation, and in a match pairs test, an incomplete observation is going to provide you no additional insight. So the last big topic that I want to discuss in this lecture is just the confidence interval for match pairs. So to estimate the difference between two dependent samples using a confidence interval, this looks very similar to what we did in the one sample t-test situation. Center the confidence interval at the sample mean of the differences, add and subtract some critical value that has n-1 degrees of freedom, and then multiply that by the sample standard deviation of the differences divided by the square root of the sample size. The assumptions and conditions for using the t-distribution in the confidence interval are the same as the hypothesis test, so I'm not going to bore you with the additional details in this case. So let's say we have 10 people who join a study that is designed to test out a new weight loss drug. Each person is weighed at the beginning of the study. They take the drug for 6 weeks with no further instruction, and then they're weighed again at the very end of the study. What we want is a 95% confidence interval for the average amount of weight that these subjects lost while using the weight loss drug. Now, taking a look at our data, column A contains the subject ID number, column B contains their before weights, column C contains their after weights, and column D contains the difference between them. Now, looking at the before weights, these subjects averaged almost 273 pounds at the beginning of the study. They averaged about 264.5 pounds at the end of the study, and that gives us an improvement or an average weight loss of about 8.5 pounds. Looking at our histograms, again, our before and after samples don't necessarily look as if they are approximately normal. The before sample isn't too bad. The after sample looks almost more uniform than normal. However, looking at the histogram of the differences, we can again see that this is approximately normal. We have one too many observations in the bin at 16. Other than that, it's very close to being approximately normal. So again, central limit theorem is going to hold despite not having 15 observations. The last thing I want to bring your attention to is the critical value down in the bottom row of the output on the left. If we use the t.inv.2t function, we know that we want 95% confidence, so we'll leave out 5% in each tail. We have 9 degrees of freedom because we have 10 observations, and that's going to give us a critical value of 2.262. Using the t-table, we would also come to this exact same conclusion, matching up the row that has 9 degrees of freedom with the column for 95% confidence is also going to give us that 2.262 for the multiplier, the critical value in your confidence interval. So going ahead and finding this 95% confidence interval, we know that we have 9 degrees of freedom. The way that we're going to set up our confidence interval is by taking the difference between our before and after means. 272.94 was our before mean, 264.44 was our after mean. Add and subtract the critical value, 2.262, times our sample standard deviation of the differences. That value from a couple of slides ago was 8.27. Divide that by the square root of 10. That gives us 8.5 as the center of our interval, 5.91 as our margin of error. So our final confidence interval is 2.59 on the lower end, 14.41 on the upper end. Now, in terms of interpreting this confidence interval, it is going to be a little bit different than what we did for just the one sample t-test simply because we are looking at a situation where we have two dependent samples. So what we can say here is that we're 95% confident that, on average, subjects who took this weight loss drug over a period of 6 weeks will lose between 2.59 pounds and 14.41 pounds. Again, it's the same general idea. You have a level of confidence, you have a description of the parameter. In this case, it's the average weight loss during the duration of the study, and then you have your upper and your lower bounds of your confidence interval. The last thing that we should address here is if there's a significant difference in the before and after weights of the subjects. Typically, when you use a confidence interval to determine if a significant difference exists, what you're looking for is zero. You're looking to see if zero is contained within this confidence interval. In this case, we can say that there is a significant difference in the weights of the subjects, and we can go one step further and say that the weights after having taken the drug are significantly low. The reason for this is that the confidence interval is entirely positive. We did the before weights minus the after weights. Because these values were positive, this was an indication that subjects were losing weight while on the drug, and because zero is not contained in this confidence interval, we can say that there is a significant difference. However, if we're looking to answer the question if this proves that the drug causes people to lose weight, this would be a definitive no. While we can say that there is a significant difference in the before and after weights, we cannot say that the drug was the cause of people losing weight. The reason here is that we failed to take certain confounding variables into consideration. We didn't give these subjects any kind of instruction as to how to act while on the drug, so they could have exercised while on the drug a little bit more. They could have improved their diet. And so while the subjects did have significantly lower weights, we cannot necessarily attribute that weight loss directly to the drug because there are other factors that we didn't control for and pay attention to over this 6-week time frame.